Okay, so now that we know what torque is and a few other things, we are ready to look at the relationship between torque and angular acceleration. Here I'd like to remind you that if you remember Newton's second law, that we had a simple relationship there between force and acceleration, and F was equal to m times a. So we'll see that there's a similar relationship between torque and angular acceleration. The only difference is that m gets replaced by a different quantity, and we'll look at that. Okay, so consider a simple example here. Now let's say that we have a system, okay, that is restricted to moving and about an axis. It's all spinning about this axis at the origin. Okay, let's call this C instead. And let's say this has mass m1, this has mass m2. Let's say this distance is r1, and then this one is r2. And there's another thing here which is at a distance r3 of mass m3, and so on and so forth. Okay, and these things are all being are experiencing some force F1, F2, say F3. Okay, and what we know is because let's assume that this is simply moving in a circle and these forces are all perpendicular to the radii, and what this tells us is that the net torque on the object is going to be equal to the sum of the torques due to each of the forces. Okay, each of these individual torques can be written as R1 times F1 times sine of 90, but sine of 90 is 1, so I'm just going to leave that out. Then we have R2 times F2 plus R3 times F3, and so on. Now, according to Newton's law, each of the forces is equal to the mass times the acceleration. So m1 times a1 for the first one, m2 times a2 for the second one, and let's also write the third term, r3 times m3 times a3. Okay, now we also know for each of these objects, okay, for the entire system rather, that the angular acceleration itself is fixed. So this alpha is fixed, and therefore for all the particles is the same, and therefore we can write the acceleration for each of the particles as simply r1 times alpha plus r2 times m2, once again r2 times alpha for the second one, and then r3 m3, then once again r3 times alpha plus dot dot dot. Okay, now here we can combine the r's and then factor out the alpha from everything else, okay, and rewrite this as m1 r1 square plus m2 r2 square plus m3 r3 square plus dot dot dot, and all things multiplied by alpha. The quantity inside the parentheses is, we're going to just call this I. I'm going to talk about that in a second. Equal to I times alpha, where we say that I is equal to the sum of these terms, m1 times r1 square plus m2 times r2 square plus m3 times r3 square plus dot dot dot. Okay, this term has a name. It is called the moment of inertia, and if you look at this, it is simply dependent on the geometry of the system, just the masses of the particles and how far they are from some origin. Okay, so this gives us the definition and also shows us how to calculate the moment of inertia for the object. Okay, and we look at some simple examples and we'll figure out how to do this in some cases in the upcoming videos. So the most important thing here is to recognize this very simple fact that tau, the torque, is equal to I times alpha. Okay, so in the next video, we'll look at some simple cases of trying to calculate the moments of inertia, and then we'll see how the moment of inertia depends on the axis. Okay, it actually, if you look at this expression right away, you know that if instead of choosing the origin, if we chose any other point, then the distances of each of the particles from that point will be different, and therefore this I will, change. So depending on the axis, the moment of inertia will change. Okay, so in the next video we'll look at that.